There you go. Van Everdingen and Hurst, or VEH method. Now remember, we talked about two methods: the small pot aquifer, which was super simple, but usually not accurate unless you have a small aquifer. Then we had the Schlitt's steady state method, which was a little bit better. The Van Everdingen and Hurst is by far the most accurate. In fact, it's more accurate than another model we'll talk about and any other model out there. It's also by far the most complicated. So we're going to spend some time on it. And that's why I want to review it. So one of the things that the Van Everdingen and Hurst uses, the method uses, is the solution of the radial diffusivity equation, which again, I like to use my roll of paper towels as a nice analogy. That inner cylinder could be the wellbore, the outer cylinder could be the reservoir, or in our case, the inner cylinder is the reservoir and the outer cylinder is the aquifer. Either way, this is a radial flow, flow going from the outlet into the inlet. And if you recall, what I told you last time was that you've seen a solution to that before. You saw it in Reservoir 1, you saw it in the video, and that was the exponential integral solution that we had for radial flow. The thing about the exponential integral solution, though, was for the case where you had a constant rate in the inner cylinder, in the wellbore or wherever. That's not what we're going to use here anymore. So we need a solution to the diffusivity equation with constant pressure in the inner cylinder, which for us is the reservoir. The outer cylinder is the aquifer. Okay, so P is equal to a constant. Well, in Reservoir 1, I don't think you learned the solution to that. The exponential integral solution was hard enough. The solution for this is even more complicated. So the exact analytical solution is the Bessel function solution. Okay, this is accurate but complicated. In fact, it's so complicated, we're not going to use it at all in this class. Okay, I don't think that most of you have seen Bessel functions before. I know I didn't until graduate school, and we don't need to use it because there are other options. Another one is the Edwardson's equations, which are a little bit simpler. They don't use Bessel functions. They use things like square roots and of time and stuff like that. So it's a little cumbersome, but it's something that you could plug into a calculator or Excel or Python or whatever. But there's a catch with that, and it's for infinite acting flow only. Okay, and by that I mean either early times or a really, really big aquifer radius, right? So that's basically when the outer boundary hasn't felt the effects of what's going on in the reservoir. So we can use those, and it's nice because you just plug it in, you get an exact number, but it is for infinite acting only, so if you're not in infinite acting, you can't use it. Another option is these plots. So we showed some plots last time of WED versus dimensionless time at different dimensionless radii, and you can just read it off the plot. And the problem with the plots is that you don't get an exact answer, right? It's really hard to get an exact answer by reading off a plot. Although I should say that it's 2021, they have computer software which it'll actually go in there and do a very precise measurement of a plot for a given x-axis versus y-axis. And then the last is the tables. And the tables are nice because they have some numerical values, but they might not be at every single TD or every single dimensionless radius, and so you might have to interpolate, which is okay. I mean, everything we do as engineers is usually an approximation anyway, so if you've got to interpolate between two things, then it's probably good enough. But regardless, any of these four methods gives the dimensionless cumulative water influx as a function of dimensionless radius and dimensionless time. And then you can find the dimensional cumulative water as the dimensional value times U times PI minus P. Okay. We did something similar for the small pot aquifer. We calculated WED, and then we calculated U and the pressure drop and did that. Here's the problem. So this is complicated enough. You've got the solution for the radial diffusivity equation. You've got to use the Bessel function solution or these plots or these tables or something. But remember that that solution assumed we had a constant pressure in the reservoir. But we don't have a constant pressure in the reservoir. As you're producing fluids, the reservoir pressure is going to drop with time. So this boundary condition wasn't right. So we have to do something to make this solution applicable. So the problem is the reservoir pressure is not constant. Okay. It might look something like this. Pressure versus time, you got an initial pressure, we'll call it PI, and maybe, you know, it declines like that, right? Put this up. Okay. So obviously it's not constant. What we're going to do is we're going to cheat a little bit. We're going to cheat by approximate. So let's say maybe at T1, this is our pressure right over here, and then you got a T2. It goes up to there, and then you have a T3 that goes up to there. And what we're going to do is say that from 0, I'll call it T0 to T1, the average pressure is between PI and this P1 over here. So we'll do a little average. We'll call that P1 bar. And then over here, you have an average, which is P2 bar. So it's somewhere in between P1 and P2, and then P3 bar is an average here. P3 bar, okay? So what we've done is we've made a series of step changes to get that, okay? So instead of having a smooth curve, it's going to be like constant for a while and then drop. And then constant for a while and then drop, constant for a while and then drop. So obviously it's not exactly what happens, okay, but it's an approximation. As I just said a minute ago, we do lots of approximations as engineers. And so in this region, so what I'm going to do is I'm going to make this right here from PI to P1 bar, I'll call this delta P1. And then from P1 bar to P2 bar, there'll be a delta P2, and then from P2 bar to P3 bar, there'll be a delta P3. And so what I'll say is that from T0 to T1, delta P experiences a pressure drop of delta P1. So it goes from this PI minus this P1 bar, and I'll show you what the P1 bar is in a moment. From T1 to T2, or I should say from T2, delta P is equal to delta P2, right? So you're going from here to here, and you get this delta P, but it also had a delta P1, right? Because the pressure has dropped all the way from PI all the way to this new pressure P2 bar. So you really have this delta P plus this delta P, or this one plus this one. And then if you go from T2 to T3.
Dr. Balhoff, could you scoot your sheet down a tiny bit?
Sure, there you go. Is that a little bit better?
Yes, thanks.
All right. So if we're going from this time T2 to T3, then delta P is going to equal to the delta P3 plus the delta P2 plus the delta P1. So you get delta P2 and then delta P1. Okay. So how do we compute WE? WE is going to be equal to, we had this equation up here, WED times this pressure drop. So we'll say WE is equal to U, but then we're going to use what's called the principle of superposition. And I don't want to make this go into a lot of mathematical details, but the principle of superposition says that you can add solutions to linear problems together to get the solution. Okay. You probably did the principle of superposition in Reservoir 1 when you talked about well testing, especially when you talked about a step rate test. Very similar, where things were changing with steps and you summed them up to get the solution. So what we're going to do is we're going to say that U is equal to WED over a time interval from like Tn minus T naught. Tn is the final time, in this case it was T3, times delta P1, plus the amount of water that comes in from Tn minus T1 times delta P2 plus WED Tn minus T2 delta P3, etc. if you had more times. Okay, so I want to explain this equation a little bit because I know it's a bit confusing. First off, this WED, this parentheses here, this Tn minus T naught or Tn minus T1 is not, I'm going to repeat, is not multiplying it. What I'm saying is that WED of that time, of that delta T, right? Because we remember that we have functions, plots, tables, Bessel functions of WED at a given time. And so what this is, it says WED is a function of this time, or this change in time. That is multiplied, maybe I'll put a little dot there for multiplication, times the pressure drop. Pressure drops delta P1, delta P2, delta P3, etc. The one thing you got to be really careful here for is where you evaluate these delta T's. So you're going to, if you notice, this delta P1 shows up from T0 to T1, T1 to T2, and T2 to T3, or all the way to Tn. That's why delta P1 is going to be evaluated by calculating the cumulative water influx from Tn minus T0. So it's the final time minus the initial time. But delta P2 only showed up from Tn minus T1. Delta P3 from Tn minus T2, right? So that's the how we do that. Now, and again, this is called the principle of superposition. And we're going to do an example problem here in a minute, which I think is going to make things a little bit more straightforward. And by the way, I'm going to do kind of part of the example problem today. I don't know if I'll do the full one, but on that list of video links that I gave you, you'll see that there is a link for examples of aquifer models, and I do the full solution in Excel on that. And so I strongly suggest that you watch that. I suspect that it'll be helpful for a future homework. Okay, so in that equation, the delta P1 is equal to the average between Pi and P1. So it's 1/2 Pi minus P1. Delta P2 is the average between Pi and P2. So it's 1/2 Pi minus P2. I shouldn't say it's the average, but yeah, that's the formula. And I show you how to get that on the PowerPoint notes. Delta P3 is 1/2 P1, not Pi, P1 minus P3. And in general after that, delta Pj is 1/2 times Pj minus 2 minus Pj, provided J is greater than or equal to 3. Okay, so if J is 1 and 2, you can just use this formula. After that is this. So if J is 3, you have P1 minus P3. If J is 4, it's P2 minus P4, right, etc. So that's how you calculate that. So what we have is an initial pressure of 2532. We get compressibility, permeability, viscosities of the fluid, etc., all provided in the top table. And then in the bottom table, we have the date, which we converted to time and hours, the pressure, which will be measured from pressure gauges in the wellbore, and then we have some production data, which at least for now, I don't think we're going to need. But what we do need is the time versus pressure, as well as the reservoir properties. So the reservoir pressure is clearly dropping with time, just as we said we thought it would. Okay, and what we want to do is to determine the cumulative amount of water that has encroached the reservoir at any given time. Okay, and I am going to do that for this time right here. I could do another time. That would be a good idea for a longer example problem, but we're just going to do one time today. So I want to know how much water has encroached the reservoir in January, and this is a real field. So this was all the way back in 1965. So that was before I was born, maybe before some of your parents were born. But this was a real field, and I was in January 1965, and I want to know how much water encroached the reservoir by that time. So after 87, 84 hours when the pressure is 2496. So let's do that example. One other thing I'll say about this is that we're going to assume infinite acting flow. Okay, so we'll assume infinite acting flow. That means that the radius of the aquifer is much, much bigger than the radius of the reservoir, and that might change what equations and plots and things we can use. So the solution and get ready because we're going to do some of this together. The solution after 87, 84 hours is given as WE is equal to U times the sum from J is equal to 1 to N, but we've only got 2 times, right? So you started at 0, but then you went to 65, 76 hours and 87, 84 hours. So times delta Pj times WED of, not multiplied by, but of TD N minus TDJ, where these are dimensionless times. And if we've only got 2 times, so we could write that as delta P1 times WED1 plus delta P2 times WED2. All right, so we're going to have to calculate a few things. We need to calculate U. We're going to need to calculate our pressure drops, and we're going to need to calculate the WEDs, but we'll need to also calculate the times, the dimensionless times, where we can calculate the WED. So, U. We did that last Friday. So we did a small pot aquifer. It was the same problem. U doesn't change. It's 2F pi Re squared HVCT, which is equal to 1415.92 barrels per PSI. Well, I think I just put it in there by accident. So 2 pi F Re squared. Yep. So thanks for pointing that out. And of course, if you have questions, then don't hesitate to ask. And we need to compute WED1 and WED2 at delta TD1 and delta TD2 respectively. Okay, so in order to do that, we're going to need to calculate delta TD1 and delta TD2, where delta TD, I'll say of J, right? J could be 1 or 2, or if this was a more complicated problem, it could be 3, 4, 5, 6, is equal to, this was in the PowerPoint notes, there's a conversion constant, 2.637 times 10 to the minus 4 times K over mu phi CT RE squared times delta Tj. So delta T is the dimensionless form, this is the non-dimensional form. And I see something in there, I see K over mu phi CT. Can somebody remind me what K over mu phi CT is? What is the variable, or what do we call it?
Alpha.
Yeah, very good. So it's alpha, which we call the diffusivity constant. And it's got units of length squared per time, like feet squared per day. All these properties, K, mu, phi, CT, and RE, are given in the table, or actually we calculated RE last time. So I'm just going to show you, I don't want to do too much busy work here, so I'll show you what I did. So we had our conversion constant, K was 437 millidarcies, porosity is 0.177, the viscosity is 0.38 centipoise. Be careful there. We want to use the water viscosity because this is a water influx model. Don't use the oil viscosity. Compressibility is 3 plus 4, which is equal to 7 e to the minus 6. And if you remember from last Friday, we calculated the effective radius of the reservoir to be 5,664.5 feet. And you square that, and this is what I get. Okay, so I just did this calculation once. It's 0.007628 delta Tj. Okay. So you just might want to write that down. That way we don't actually have to do the calculations again. But so then delta TD1 is equal to 0.007628 delta T1. Okay, now this is where we'll start doing this together. Think about it for 30 seconds. What should delta T1 be in this problem? Okay, think hard about what I just tried to explain a minute ago. I don't know if anybody got that. So it's actually 0.007628 times 8784 minus 0. And that gives me 67. It's dimensionless, there's no units. Okay, I don't know if anybody got that, but that's a very easy mistake to make, and it's really important because everything's going to be wrong otherwise. Delta TD2 is going to be 0.007628 times delta T2. Now, what do you think delta TD2 is? Yeah, so we're here, this is the final time, and the times are 0, 65, 76, and 87, 84.
So wouldn't it be, so if our T1 was from, or was that 87, 84 minus 0, wouldn't it just be going 87 to 84 minus 65, 60, or 76?
Yeah, that's exactly right. So it's 87, 84 minus 65, 76. And if I plug that in, I get 16.8 dimensionless again. So good job, Victor. Okay, so now we have these delta TDs. We can use those to calculate WED. And remember I told you that it was infinite acting, so I don't have to worry about what the dimensionless radius is. It's only a function of delta TD. Now what I want you to do is calculate WED of 67. And I'm going to ask you to start by using the plot. Okay, so TD is 67. So what is WED? Doesn't have to be perfect, just give your best estimate as possible. So you'd use that top line. Very good.
It's about 35 then, give or take?
Yeah, I got 32, but 35 is close enough, right? So I said 32, and this is from the plot, right? So I went over here. This was 50, this was 60, this is 70, so just try that. I went up and went over, and yeah, you know, somewhere between 30 and 35, I said 32. Okay. And then I did the same thing for 16.8. It's a little bit more challenging. This is 20, so maybe right over here, come over, right between 0 and 20, maybe a little higher. So I estimated 12 on the plot. All right. And the infinite acting table is much easier to use because we don't have to worry about the dimensionless radius. So what we have is this table, and we have TD in the left column versus, well, they call it QD. This is from a different textbook, but it's WED for our purposes. And I will give you a moment to look at that, and then you tell me what you get for delta TD is 67 and maybe 16.8 as well using the table. Good, 31.308, which is pretty close to what we estimated from our plot. And then what about 16.8? Did anybody get that? So the time is 16.8. Well, that's not in the table, but they have 16, which is 10.4, and 17, which is 10.913. And if I wanted to, I could do a linear interpolation and do the calculation and everything. But I'm really lazy, and I like approximations, so I'm going to guess about 10.8. Right? So it's obviously closer to 17 than 16, so it's closer to 10.9 than 10.4, so I don't know, it's about 10.8. I bet if you did a linear interpolation, you get really close to that. Okay, so hopefully you all got that. Now I would like to say one last thing, and that is that I did this one other way, which is to use these Edwardson et al. Equations right here. And there are three different equations. You got to be careful. So TD is not less than 0.01, but it is between 0.01 and 200. So I use this middle equation. Oh, it's a little cumbersome, but if you plug it all in, then I get 31.17 and 10.82 from the equation. Okay, which one do I use? Use any of them. Okay, use any of them. They're all close. Okay, it's good to do maybe more than one to make sure you didn't make a mistake. But you know, we're making approximations here. So that's what we get for our WED. Then we have to calculate delta P1 and delta P2. So delta P1 is 1/2 Pi minus P1, which is 1/2. The initial pressure was 2532 psi. And the pressure at the first time step was 2503 psi. So I get 14.5 psi. So that's the pressure drop between the initial pressure and that, or it's the average pressure drop. And then delta P2, if you look into the equation, is 1/2 times P1 minus P2. You need to be careful though, because the pattern kind of changes a little bit once you get to delta P3. We're not going to use delta P3 today, but if you did, then that would be the case. So it's 2532 minus 2496, and I get 18 psi. So we are running out of time. We've got 30 seconds left, so I think I'll stop there. But that's unfortunate because I'm very, very close to finding the right answer. So what I would suggest is that maybe right after class or over the weekend, you do this final calculation, and I'll give you a hint. The answer is 918,000 barrels at this time. Okay. Now, one thing you'd have to do is to redo this calculation at all the other times if you wanted to figure out what the cumulative water produced was or encroached was as a function of time. Okay, but 918,000 is the answer, and you just plug it into this equation up here.